Hi everyone, John Olick here. Back in 2008, when I worked at id Software, I did a presentation at Siggraph about real-time ray tracing. Voxelnauts' rendering technology is based on that. And so I wanted to put the full presentation up here in all of its unedited glory for you guys to learn more about how our rendering works. Keep in mind though that this is highly technical and meant for a very technical audience. Thanks, and please support our Kickstarter.
So in the next generation, and even in the current generation, entity processing is by far the most sequential part of the game code. Typical code involves processing each entity one at a time. A next generation engine, however, should plan for parallelism. Now, double buffering the game data can achieve peak performance by allowing each entity to run asynchronously. This does force certain rules in the processing, however. Each entity can only read from the previous frame's results, and each entity can only write to itself. This approach has certain unique benefits. You can implicitly record the progress of a game and replay any frame to debug it. To help find bugs, you can also switch back to a single big loop and randomize the processing order. And protecting the memory can enforce the reading and writing rules with hardware exceptions. In games, however, there will be times when entities do have other dependent entities for a single frame. In these, hopefully few cases, you can run them in a separate batch after all previous entities have been processed. This does create synchronization points in the processing of entities, which hopefully there won't be too many of. So let's boldly go where no game company has gone before. But first, why raycasting? That's a good question. Back in Quake 1, if you had to make a decision between having an additional processor or having a GPU, which would you choose? And why is this any different today? So that's a little misleading. Due to the fact that early rasterization hardware could process a pixel per cycle, a single additional CPU would not match the improved performance of a GPU. So it really comes down to price. You get faster hardware that can do the same thing for less money, and I do believe that this is still true today and for the foreseeable future. However, as hardware becomes more programmable, uses other than rasterization are possible. Although using the hardware for things other than rasterization will be slower, simply because the hardware is not designed for it. Once a proof of concept is out there showing the value of something like raycasting, specific hardware that really accelerates it can then become a viable money-making strategy. When that happens, the hardware will be built with that in mind, perhaps by adding some fixed-function hardware. At this point, though, raycasting technology is far too infant to determine any common patterns worthy of hardware abstraction. It's just too risky. So the answer, of course, is that it's not. What value does raycasting provide to game developers? Well, as is evident in the last half of this presentation, much of the work in making games goes into optimizing for performance, fitting everything in memory, and most importantly, content generation. But what if you never had to worry about triangle counts, so that the model that the artists create in ZBrush were the final models? What if you never had to worry about rendering performance because it was fairly even, no matter how complex the view was? And what if you never had to worry about the memory footprint of your textures or geometry as it streamed in from disk at the highest level of detail that you can perceive? Now, while all these things are possible with rasterization, they are easier with raycasting. So the answer is shorter and cheaper development with higher quality games. So what value does it provide to end users? We are making a bet that it will provide good value. However, until it's realized, there's always the risk that it won't pay off. I do believe that it will pay off in spades, and here is why. What we've seen in Rage with unique texturing on every surface and the drastically improved quality level from that, we can also see a few areas of improvement. So as we can see from the screenshot, while it looks great, if we take a closer look at the oblique surfaces, we can clearly see that everything is flat. Even though the textures and normal maps say differently, this is clearly a flat surface. And this is even more evident when in motion. But with raycasting, we'll be able to, like a pop-up book, make the apparent geometry become real geometry. So there is some real value that can be added here to practically every surface. The content production pipeline doesn't really even have to change very much either from a unique texturing perspective, because you continue to stamp detail, where the detail is created from high poly models. So just briefly, the speed up of a program using multiple processors in parallel computing is limited by the sequential fraction of the program. For example, if 95% of the program can be parallelized, then the theoretical maximum speed up using parallel computing would be 20 times faster, no matter how many processors are used. So why is raycasting better for Amdahl's law? So let's take a trip to the future of rasterization to show a possible course of how this will play out. In this diagram, triangle setup is by far the biggest sequential element of rasterization. And the problem is only going to get worse as games will use smaller and more triangles. But if you remember from earlier, a lot of the performance benefits of SPUs were gained by insisting this particular part of the GPU. And certainly future games will be doing the exact same thing. Let's take a look at how the hardware vendors may overcome this. Now, if we subdivide the screen into multiple regions, we can then process each of those regions in parallel. Now, there is a diminishing return problem with this. So as the screen gets split more finely, the overlapping triangles will have to be set up twice. However, I don't think this is going to be a huge problem, because the amount of screen splitting will likely naturally follow the reduction in size of triangles and not precede it by much. There are two primary ways that the hardware vendors could implement something like this. The first of which is by duplicating the GPU into multiple cores. This has a problem, however, with sequential reads of the triangle index buffer, which the GPU reads one at a time until all triangles are iterated. Now, the second way is to the addition of a triangle sorting stage, which sorts the triangles into those parallel regions of the screen. You can parallelize the sorting itself by dividing the input triangle list into sections where the number of sections is equal to the number of available processors to work on the data. Now, this certainly is a valid technique and will serve the hardware vendors well for many years to come. However, the long-term success of this algorithm depends on the core count keeping up with increases in render resolution. There also may be some dependencies on bandwidth. But there is no current indication that this will ever happen. If it did, it would probably be due to hitting atomic limits in the fab process. Even then, though, three-dimensional lithography would demolish that barrier. So rasterization is here to stay for a very long time, or at least something like it. So I'd get used to it. In the short term, however, graphics cards are not easily capable of displaying the kind of triangle counts that can rival a raycasting approach. So there's a third option here that could benefit both raycasting and rasterization, not to mention a myriad of other GPU compute techniques. In this option, we're going to need random access to the triangle index data so that the total number of triangles is almost irrelevant to performance. So how do we do this? One answer is a preprocessed or dynamically updated spatial data structure, which would convert the problem into a binary search, where for each pixel, the data structure would be intersected with the ray to gather the input for rendering that pixel. Now, this process is very similar to raycasting, obviously. And what's interesting is that if the control flow of the tree structures of all the various different things could be standardized and abstracted slightly, then they could all use the same thing. And so raycasting could piggyback on the technology and may be an interesting win-win approach for the hardware vendors. So why voxels? There's so much momentum with triangles. Why change, and why now? Now, Rage certainly proves that unique texturing is possible with existing technology, and I spoke about progressive mesh in the previous half of the talk. That seems like a decent solution to the unique geometry problem, although there's plenty of others, such as displacement maps or, subdivision surfaces. But here's the dirty secret to progressive mesh. It's in the content generation. Now, the triangle collapsing solution tries to be automatic and does a decent job at it. However, it still requires an artist's touch to tell which edges are important to keep. This can be a very time-consuming, iterative process. More man-hours means more money, whereas the voxel approach solves both problems at the same time, well, hopefully without requiring any hand massaging of the data, which of course equates to real dollars and cents. So why is the control flow of raycasting efficient? So if we have a few rays over here to trace against that sphere over there, we can see that as they traverse through the world, they generally follow the same data up until the last few recursions. But what if the camera was really far away, so that the ray endpoints were really far apart? Then the data axes would be much more scattered in memory, wouldn't they? Well, if we stop traversing the structure when the size of a voxel is less than the size of a pixel, then much of that data coherency is maintained and very little detail is lost. So through this, there is a geometry mapping of sorts. There are artifacts that occur, though, when you have two walls very close together of different colors. For example, if one wall has a shadow and the other wall does not. You can kind of have this incorrect bleed-through effect, which can be mitigated in various ways. For example, by instead of using colors, using spherical harmonics to get a color based on a viewing direction. But just saying don't do that to the artist should hopefully be sufficient. Although primary rays have this really nice access pattern, secondary and tertiary rays don't always have coherent patterns. Luckily, important sampling comes into help here. However, for the next generation renderer, baking in most of the secondary information is probably preferable. So the sparse voxel octree is the data structure of choice. Now, octrees are a form of compression related to run length encoding. Variable splitting planes are useful, certainly for optimizations, as well as for patching the bleed-through artifacts. Now, there may be some interest in trying KD trees eventually as well, but I'm kind of concerned in a few different areas about that, which I won't go into. These octrees are going to be very large, on the orders of tens of gigs at least. So a paging system is necessary to fit it in memory, even for next-generation consoles. But before I talk about how to do this, let's ask the question, is this really a valid lever that we can use? So as we can see from this graph, the size of a hard drive increases by an order of magnitude every 5 years or so. And by the time the next generation of consoles is out, hard drives will routinely be multiple terabytes in size. Now, consoles generally lag behind this curve a bit to save on cost, but a 500 gigabyte hard drive for a next generation console is certainly not out of the question. Now, the virtual pages are organized in an octree, and each page is itself an octree. So from scratch, start with a single page and add voxels to it until it reaches a capacity. Then split that page into 8 subpages and attempt to add the overflow voxel again. Then at runtime, you only load as many levels of a page as necessary. The capacity is flexible and can be derived from practically any parameter, including the ones listed here. If the pages are not of a constant size, the on-disk cache can fragment. As pages get added and deleted over time, solving this is fairly simple, though. You basically just copy the data from one file to another and remove any empty space that's not being used. But more pertinently, there's also problems on the runtime side if you're dynamically allocating fragment space in the arrays, or not fragment space, if you're dynamically allocating nodes. And this can be solved by, for example, by bucketing the nodes into certain sections based on which page they're in and the particular properties of the page. So most algorithms that execute on an octree representation instead of an array representation have an execution time proportional to the number of blocks in the volume rather than the number of voxels. So in this way, octrees are somewhat like a dimension-reducing device. This also reflects that the amount of space occupied by an octree is sensitive to where it's positioned. So it can be shown that translating the octree by 2 to the power of any number does not affect any node smaller than that. And through this property, we can develop the following method to optimize an octree. It exhaustively tests all meaningful translations, keeping track of the number of nodes at each step and choosing the best one. Okay, now just to help hit home how important this is, here's a diagram showing a typical worst case where the translation of data will really help. And if this quad tree is shifted to the left or to the right by 1, then it consumes almost half the number of nodes. But we can take this one step further here. If we know the difference between the outside of an object and the inside of an object, we can also tune for the minimum number of outside nodes, thereby improving runtime performance. For example, here the outside nodes are white and the inside nodes are gray. A casting array vertically here will have a costly performance hit. However, if we translate the data 1 unit to the left, the performance cost is significantly reduced. If we don't have intelligent storage formats, the offline storage costs will be enormous, probably on the order of hundreds of gigs. As such, the editing and runtime data structures will be different. The editing will be optimized for disk speed, whereas the runtime will be optimized for display performance and size. So this is the current runtime data structure. Now, while it is possible to compute the normal from neighbor voxels, it is a bit expensive to compute at runtime, requiring up to 26 additional traversals of the tree, or storing neighbor pointers for perfect accuracy. Or you could approximate the normal by looking at the immediate siblings and only doing a single upwards traversal. It's probably better, though, at this point, just to spend the extra data and pre-compute it. So for the storage data structure, the child pointers are now a simple bit mask, where the ordering of the nodes is assumed by the compression and the decompression functions. So it's kind of like an arithmetic compressor in that sense. So how do you compress the gigs or possibly terabytes of data down into something a little bit more manageable? Compressing this data is a simple 3D extension of some compression technology I was working on, and it breaks down into 2 separate problems. Problem number 1 is compressing the child bit masks. So here you can see, if we plot out the statistical distribution of the child bit masks, we can see that they have definite patterns that we could take advantage of. But we can take this step 1 step further. If we separate out the bits by level of the octree, the distribution varies from each level. The distribution varies from the average at each level, which allows for further compression. So in summary, for each level, gather the bits and perform entropy encoding on the pieces. So compressing the color data is a process very similar to wavelet compression if it were applied to 3-dimensional data. You take each level of the octree and subtract the value from the higher level. So each octant's color data becomes a delta of its parent. So in summary, split the colors by level, quantize them, and then entropy encode them. Now, a somewhat similar 2D technique produces a 24-to-1 compression ratio on average, with the worst-case noisy sections compressing 12-to-1. A conservative estimate here is that the 3D data will compress at about an 8-to-1 compression ratio. And I think we can definitely hit that, but a lot more research needs to be done in this area. So it costs an additional 15% of data for the geometry bitmaps. And the smaller an equivalent triangle gets, the better the cost savings will be if you used voxels instead. There is 160 bits per triangle in a float format, and about 80 bits per triangle in a typical compressed format. Now, if there are 32 times the number of triangles in a next generation game over a current generation game, then each triangle costs about 72 bits if it were voxels, which is about a 2-to-1 compression ratio with the traditional format and about equal to the compressed. So when generating the voxel octree, it is important to note that any surface can enumerate to voxels, whether they be fractals or triangles. Triangles enumerate to voxels through various different methods of 3D scan conversion, the first of which is an evolution of 2D scan conversion to 3D. Here, each third-dimension slice of the triangle creates a 2D polygon on that slice. And to accomplish this, you find the longest 2 axes of the triangle, scan convert in 2D along those axes, and then offset in 3D along the shortest axis. Another approach is to create a bounding box around the triangle, and for each voxel, test to see if it collides with the triangle. Then at each voxel, using barycentric coordinates to reconstruct the other properties, such as texture coordinates. But care must be taken with this approach, as the center of a voxel can lie outside the borders of a triangle. And this is important, for example, when you're reconstructing the texture coordinates, they could be like off in space. Yet another approach is to subdivide the triangle and ensure there are no cracks by simply comparing the voxel space locations and making sure they're all touching. And if not, subdivide again. However, this approach has problems with jittered sample locations, which are not regular along the triangle. And this technique is really easy to implement. It's the one that I'm currently using. Triangle voxelization sometimes creates voxels inside of an object which can never possibly render. To fix this, you use a mark and sweep filling algorithm to call out any unnecessary voxels. To generate the geometry bitmaps, you recursively average the colors of all 8 children together. Pretty simple there. The next step is to perform ray tracing to light the voxels. This requires 2 sets of data, unlit data and lit data. You probably want to keep the unlit data around in case you want to relight your scene at any point in time. So to use the data, what you do is for each pixel of the screen, you shoot out a ray into the octree and write out the node number, not the color. If we want to mix ray casting with standard rasterization, we're also going to need to output a depth buffer. To trace a ray through the octree, you clip the line against the mid-planes only. In its most optimal form, this requires 2 lookup tables to determine which nodes the ray intersects, and the other to find the order in which the ray intersects them. Now, I found this method turns out to be faster for CUDA than the stackless methods that I've tried, but I haven't tried any stackless methods which require neighbor pointers because of the memory restrictions. One of the key problems that I've yet to talk about is when do you load additional detail levels, and when do you stop casting because the size of a voxel is less than the size of a pixel? So the straightforward way to do this involves, during the traversal process, computing the size of a voxel and comparing it to the size of a pixel. And while this works great and produces excellent results, it also means that we're rendering a lot of data that we'll never really see on the oblique angles of surfaces, which causes us to load that additional data as well, impacting streaming performance. So I'm going to suggest a different technique that fixes these drawbacks. So have the raycasting output the node indexes themselves, then in a post-process, compute the number of pixels per node, and if the ratio exceeds a threshold, you load up an additional detail level. It's very simple, and it works great. This improves performance by up to 20%. To fix the situation where you can jam your head into a wall and see the pixelated voxel cubes, which I'm sure a lot of people are concerned about when people say voxels, is what you can do is you can use a post-process blur where the width of the blur kernel is related to the size of the voxel on the screen, which is really easy to compute since you already know which node is at a particular pixel since you wrote that out instead of a color earlier. So how do you render dynamic geometry using raycasting? There are at least 2 ways of doing this. I'm sure there's more. You could raycast against or rasterize a coarse triangle mesh, then transform the raycasting back to the original base mesh where you would then collide with its local octree, which would also enable the instancing of geometry. Alternatively, you could also dynamically generate an entire side octree every frame, which is separate from the main octree, render the scene twice, and then merge the results. However, if you don't require perfect shadowing in your game, it would probably be faster for current generation hardware, and I'm thinking that it's going to be faster for the next generation of consoles, to use a hybrid approach and render the characters and its shadows using a traditional rasterization method similar to deferred shading. There's a particular optimization that is possible if you generate a coarse hull of the geometry and render it through standard rasterization. Using the depth information from that coarse hull, you can then move forward the start of the raycasting to the depth that was rasterized. Now, I did some preliminary tests using the previous frame's depth buffer to do almost the same thing, and the rendering kernel was up to twice as fast. Another side benefit is that the traversal process was much less sensitive to scene complexity. So this optimization is important when the camera is looking at lots of oblique surfaces, which causes lots of rays to almost intersect those surfaces without ever actually hitting them. It also is important when the camera is very close to a highly detailed wall, which it may not even be looking at. For example, if you're way jammed up back in the surface, every single ray on the front of the screen will almost hit that surface but never hit them. It's like your worst case scenario there. But it's actually quite common when you get a full scene in. Another interesting thing that you can do is adaptive subsampling over the scene. No surprises there. That's pretty standard. Of course, there's problems with the approach, that you're always sampling the most divergent parts of the scene and hence the most expensive to process. This can be mitigated through various sorting and chunking methods, but not really eliminated very easily. There's also all sorts of other cool Monte Carlo sampling effects that you can do to do motion blur and things like that. So specially designed recursive octrees can be appended to the leaves of an octree, which can simulate a near infinite amount of detail. You can simulate many different types of surfaces. Alternatively, you can programmatically generate additional surface detail as well. So how much time is it going to take to come up with a really robust solution here? And I think about a year on tools and about 3 more months on runtime. And I expect to use at least 1/3 of the rendering time on things other than raycasting. So in order to run at 30 frames per second, we would have to render the entire scene in under 20 milliseconds. And while this is theoretically possible on the GeForce 8800 series, reality does fall a little short here, and 15 frames per second is more likely. Although I am working with NVIDIA a little bit on that. How would this affect a platform launch? What this technology effectively provides is a generational skip in geometric complexity. With next generation platforms likely being at least 4 times better than current generation technology, 60 frames per second at 1080p with anti-aliasing is definitely reasonable. So I'd like to thank all these great people who helped make this talk possible. And thank you all very much for attending. But I'm not done. They say that seeing is believing. And so now I'm going to show it to you. Check and make sure something's set up properly here. Yeah, okay. So this is Imrod by Dmitry Parkin. It's a 7 million polygon model running at 60 frames per second. It's silky smooth. It actually runs a little better than that here, but it does drop down to 30 frames per second at some points in time. It's running on a single GTX 280. Currently, it's rendering at 1024 by 768, and there's no real reason why you couldn't run at a higher resolution. It's just kind of what I was told that these projectors supported. So I'm going to zoom in on the face, and you can get down to the polygon level. So as you can see, there's no cheating here. It's dynamically streaming in the detail levels, doing all sorts of optimizations to make sure that it's pretty picture perfect. And for the most part, it's pretty unnoticeable. So what I'm going to do here is I'm going to strafe, which is the worst possible thing that you can do. And the reason why strafing is bad is because the game has no idea what's coming next. It's like the worst case scenario. Oh my God. The only thing worse would be teleportation. And Yes, yes, teleportation. And I definitely don't handle that gracefully. But this is actually quite good. And this tests like just how good the streaming is on here. And as you can see, I'm just going to like stream and over here. And as you can see, it's like high detail. You can't even see it. I'm going to try to make this as worst case as possible so so you can get down and on there. So all the shadowing here is baked in. This isn't like real-time dynamic lighting because all you really have is like a color per node, right? So, but you could do like as complicated shadowing as you want here. You could do your photon mapping, or you could do all sorts of different types of ray tracing and get it looking really darn good. So now I'm going to zoom in on his hand, and you can see that all the nails and wrinkles on his hand that the artist put into to the thing. And you can actually zoom into the detail there on that. Yeah, I'm sorry for the crappy mouse. I just didn't have a whole lot of time, by the way. But looks pretty good. Oh, by the way, this is not IDTech 6. This is just something that I've been working on with my brothers for the last few months, specifically for this presentation. So now what I'm going to do is I'm going to display the node indexes. And this is kind of what I talked about earlier, where you do the two render passes, where you convert you render out the node indexes, and then you convert those into colors at a later point in time. And so through this, though, what you can see here is you can see the loading as it actually happens, and so there's no cheating going on. And I'm just going to kind of like prove that to you, that it's actually going to stream in, and then I'm going to back out, and it's going to stream out the data. So this kind of shows that the technology definitely works, and it works exceptionally well on existing hardware. Now, there are certain challenges that still need to be met and released, for example, by rendering an entire world, which is largely not a problem of the algorithm. It's largely a problem of available video memory, actually. So, but that's the end of the demo. I hope you enjoyed it.